Well, well, keep making the wife behind you smack me one. Thank you. Okay. Okay, good. So our second speaker, second members this evening, is Les Brand, who you all know. Just in case those who don't, Les is an astronomer, an astrophotographer. He works at the Royal Observatory Greenwich, and he's also a STEM ambassador, science, technology, engineering, mathematics, guidance to youngsters. And most importantly, he is our outreach officer, where we have all the various presentations we give to the youngsters, different groups that come here. Les's talk this evening is the Variable Stars Part 2. This is a follow-on from the talk that he gave, not just to us last year, but also at the Essex Mini Astrofest. Those who went along to St Bernard, Les gave the presentation there, which you will receive. And he's going to basically be updating us on the observing and measuring variable stars, new data for the Type II Cepheid variable from the 2mm Liverpool Telescope, and also explain some of the many stellar characteristics that can be obtained by simple photometric observations. So, over to you, Liz. Thank you. Thanks. You need one?
Yeah. Right, brilliant. Right, good. Okie doke. Right, so well, welcome everyone, and thanks, John, for what a brilliant talk. Eh? How am I going to follow that? Honestly. Absolutely. Shall I sit down there? Shall I sit down there? Yeah. So apologies in advance for those of you that went to the Mini Astro Fest at Burnham on Crouch, which was set up in collaboration with other Essex astro societies. I gave a version of this talk. I've added a little bit to it, so I think some of you, hands up if you went to that. Oh, crikey, more than I thought. All right, okay. Anyway, I've added some data to that, and for those of you that didn't go to that, but I think it's about 2 years ago now, I believe I gave a similar talk when I was sort of starting out. So some of this is based on a project that I did for my degree that I've recently completed on astrophysics at the Liverpool John Moores University, which is the reference to the Liverpool Telescope. So some of the data that you'll see I actually got from that, but, and perhaps more importantly for us here, a lot of the techniques and approaches to capturing data along the lines that John was talking about with all the professional telescopes actually translate very well to what we can do with our own equipment, even at the level of a DSLR camera. So on the one hand, you hear a lot of sort of professional stuff and all that research quality, but a lot of research is being added to by the so-called citizen scientists, i.e. you guys in the room potentially, by some actually quite straightforward techniques. So actually, hopefully what you'll get from this is a little bit about variable stars, transient objects in general. So some of the things that John was referring to, the very time domain or transient astronomy is the place to be. Quite honestly, it's stuff that varies very quickly or slowly, and how can we keep track of that? And where the citizen science stuff where we can come in is by adding to that. So things like light curves and stuff like that we can contribute. And very often research groups put alerts out along the lines of exactly like John was saying. You get something happens or that there's a research program going on, and the teams will actually not just contact other professional telescopes, but contact amateur groups and say, could you point your telescopes or your equipment to this area in the sky and do some photometry data? So we can actually do that. Thank you very much. So, right, okay, this is where I need somebody over here. No, you're all right. I've done it. Hopefully it will work. There we go. There we go. So, without reading the bottom of what it says at the bottom, can anybody tell me what this is? Peter, you can read it. I don't, not you, not Peter. Anybody else? Somebody towards the back. Car headlights. Yes. Can you spot the deer in between? It's two images of Betelgeuse. And remember, just only a few years ago, about 3 or 4 years ago, there was a sort of, what's going on with Betelgeuse? It's dimming. You know, Betelgeuse, like a lot of stars that's finished its position on the main sequence, become a red supergiant star, is doing strange things. It's big, but it's big and it's sort of doing that. And occasionally it does that and other things happen. And that was happening, and Betelgeuse was sort of dimming quite a bit. So that is a type of variable object. And it's transient in the sense that things are changing in time. Here is something else. This is perhaps a little bit more obvious. This was last year. This was supernova 2023 IXF, which was first thought to be a type 1A. But it then became apparent later by techniques of photometry and spectroscopy that actually it wasn't a type 1A. It was exhibiting different types of things, but it was actually you can spot it, you can look at it. And in fact, I think Ian and Jackie aren't here, but I'm pretty sure Ian was imaging M101 last year and did actually catch it, the before and the after. So in some of his images, he could actually catch that glow, that fantastic amount of energy that's just been thrown out into the universe, which fundamentally is more energy or more power than is being produced by that entire galaxy for that small amount of time. I learned on my course, astrophysicists have wonderful, they invent new terms. They measure energy not in joules or ergs, but in supernova they call it a pho. Yeah, and if I can remember what on earth it means, it's something to the power of. It's just a shorthand, but it means an incredible amount of energy. Right, and you can see that was Wednesday the 17th of May. Nothing there. Saturday the 20th of May. All of a sudden, something shines up. So people amateurs who are just doing imaging, because we like doing imaging, can actually spot these things happening. And there are a bunch of amateur astronomers out there that spot these things. There's a Japanese guy who's been quite prolific in spotting supernovae. Now, we all know about variable stars. Hands up, we all know about variable stars, don't we? Yeah, we've heard of variable stars. But actually, there's a sort of a zoo, if you like, a variability zoo, which is tree in this case. But there's lots of things that are on the face of it variable objects, and we sort of, astronomers group them into two different types: extrinsic, things that are happening to an object, but aren't happening to things that are affecting or let me start again. Intrinsic objects, intrinsic variables are things that are physically, fundamentally happening to that object that causes its brightness to change, and it's actually part of the actual object as well, the physics of actually what's going on. And then there's the extrinsic, which are sort of like one thing moving in front of another, like an eclipse, for example. That's not it. There's nothing intrinsically happening to the sun or the moon. But actually, when one moves in front of the other, and let's hope it's the sun, the moon that moves in front of the sun, otherwise we're in trouble. That would be classed as an extrinsic event. So, you know, asteroids, as they're rotating, they're not physically changing anything, but they're rotating, so they're reflecting different amounts of light, and therefore their variability changes, and so on. As you can see, there's an incredible sort of breakdown of all these different objects. I would just cover a few of them, but the ones that, for my project at least, and what a lot of amateurs are interested are sort of pulsating stars. You know, the classic variable stars. But you can see all these things in green. These are all within the class of pulsating stars. And there's a huge sort of classification. And the classification is really dependent on the physics of what's happening. The physics of what's happening, you know, the type of star, the type of physical processes that are going on inside the star. We tend to think of our star, the sun, our closest star, as pretty quiescent. You know, it looks, you know, it's in the sky, it's not really doing much. Actually, we know it's doing an awful lot. But it's on the main sequence. And so it's just doing the same thing over and over and over again, burning hydrogen into helium for the next 5 billion years or so, until it then decides not to do that anymore, and it comes off the main scale and starts to do other things. And when it starts to do other things, that's when these interesting things happen. There's also cataclysmic category, which is where we get to supernovae, you know, things that blow up. And other things like novae, and Peter, I think, has done a talk about novae and about, you know, these new stars that suddenly erupt in some way and get brighter, but then dissipate, and then nothing might happen for, well, again, in our lifetime, or they might do that every so often. And there's physical mechanisms at play that are very often due to the life cycle of that star. It's typically a dwarf, a white dwarf star, but it has a companion star, and that companion star and that star interact and do various things. I'm not going to go into the details of that right now, but as an amateur astronomers, we can measure the intensity, the brightness. We do that all the time when we're capturing our photons, and we can do that for a lot of these things, the brighter objects. So here is one such. In fact, this was the first variable star to be observed. Way back now. Peter, you'll tell me the history of Myra. That was a few hundred years ago now. It was first.
It started in the 1780s.
Thank you. So
I think it's been noted, but there's an incredible variation between very naked eye visible to the undermount and 22.
Yeah.
So I think it will probably be in an ancient time, wasn't it? But nobody knew what was
no, nobody would have really noticed it. But you know, and there are others. But Myra variable, and what is happening over a certain amount of time is, well, it's getting bigger and smaller, and you can see here, as it's getting bigger, the number that's showing on the left-hand side is the temperature in Kelvin, and as it's getting bigger, the temperature drops. And over on the right-hand side, we can see the radius of the star. Okay, and that's doing it quite regularly. But Myra is what we call a long-term variable. It changes over you know, an incredible long time. And some variable stars actually change very, very quickly. But that's what's happening. And why does it pulsate? Well, again, there's a whole sort of theoretical basis of why stars pulsate, but effectively our sun does change its intensity a little bit, a few percent, but it's not what we would call a pulsating star. A pulsating star is one that has gone beyond its main sequence by and large. Main sequence stars, they're in what we call hydrostatic equilibrium. So you've got the nuclear fusion that's going on at the core, and that's creating the radiation that's coming out, and that's radiation is a pressure. The pressure, just like a gas in a balloon, similar, analogous to that. But also you've got the gravitational force that's trying to pull everything in. And actually that balance is really where our star, the sun, is, and all main sequence stars. But what happens when a star uses up all of its hydrogen and starts to sort of become more of a shell burning type star? It shifts off the main sequence into a different region on our wonderful Hertzsprung-Russell diagram, which I think I will show you in a minute. But what's happening is that radiation pressure is changing depending on where in the star different physical things like fusion and so on is actually happening. And so what you see is different regions within the star exhibit different amounts of pressure, radiation pressure, and sometimes the gas gets very dense, which helps the radiation pressure. It's sort of pushing things out. And that is offset by gravity, which is sort of too weak, so the pressure pushes the star out. The star grows in size and becomes brighter. And then actually gravity then takes over, because once the pressure has got to the outer reaches of the star, it's less powerful, if you like, but gravity takes over and starts to pull it down, so the star shrinks and therefore becomes dimmer. And it keeps doing that over a cycle. So that's in a few words what's on here. Yeah, here's our Hertzsprung Russell diagram. So sort of up here, snaking from the top left to bottom right is the main sequence, and you'll be familiar with the positions of, I mean, the sun. Where is the sun? Well, the sun will be down here somewhere in the dwarf region there, with G round about there. But what happens is there's this, what we call an instability strip. The instability strip is where stars that are in that region are doing that. You know, they're unstable. And depending on where the star is, depending on the progenitor star, where it was on the main sequence, gives rise to different characteristics, and therefore gives rise to different types of variable stars. And then, you know, you can look at how the population changes. And when you're seeing a variable star, it's sort of, where's the magnitude? For magnitude, you can also look at luminosity. It's basically making small movements like that. So it's actually changing in luminosity. Okay. Now, some of these types of stars have interesting characteristics. And I'm sure you've heard of Cepheid variables. Who's heard of Cepheid variables? Okay. Hands up if you've also heard of a lady called Henrietta Leavitt. Okay. Let me tell you about Henrietta Leavitt. Henrietta Leavitt was one of the, not astronomers, she was a computer at Harvard Observatory back in the turn of the century, and was poring over glass plate images, not our wonderful digital memory cards that we can do blink comparisons and things, and noticed that there were specific types of stars that seemed to exhibit a change in brightness, or the period of the change in brightness, specifically the period. So going from the brightest down to the dimmest and back up to the brightest, that would be the time period. And because they were using at the time a method of finding distances of stars called parallax, so for the closest stars, they could actually measure the distance through basically Pythagoras' sort of triangle method, they could work out the distance of these stars, and hence not just measure the apparent magnitude, but measure the absolute magnitude. And then what she noticed, that there seemed to be a link between the absolute magnitude and the period. And that's what's represented here in this chart here. And these are all her sort of data points. So we've got along the bottom the period, and along the top a sort of a measure of luminosity or magnitude. Make this a little bit clear. This is from her original paper that she put there. I'll come on to this in a minute. Perhaps a slightly clearer diagram. So what we've got here, if I go back to this one, is a straight line relation. A straight line relationships are pretty good, because you can start to infer things from those. power law relationships are also good, and astronomers are always looking for these types of relationships. But what they found, and what she was looking at, was this sort of orangey yellow line, was there were lots of stars, and depending on the period, there was a relationship between the luminosity, how bright the star was on average, with its period. And that was a very linear relationship. And that then gives us a clue, because if you can calibrate this chart for some of the closest stars that are working in this way, and this is where they became known as Cephids, the Cepheid variables, you can then use this information to look at other stars that you notice are varying in brightness, and provided you know that they are the same type of star, which is a big caveat, but let's assume that you can say, I know that this star seems to be varying in brightness in a particular way, and I can measure its apparent magnitude, and it's a long way away. I don't know how far away it is. Well, actually, if I know how it's varying, what the period of its brightness change is, I can then just read off the chart. So if I see a distant star that I don't know its distance, I can read its period, work out its absolute magnitude as we've measured with calibrated stars closer to us, and then using a simple relationship, and here's like a worked example, use something called a distance modulus, which is actually probably the most complicated equation you'll see. Actually, it's really simple, but it's apparent magnitude small m, absolute magnitude big M, which is what we've calibrated the star at. And just by using those two measures, because we know what the period is, so we can read off the big M, we're measuring the small m by our telescopes and calculating that, and then rearranging this equation, we can then work out d, the distance to the star. So we've now got a way of measuring distances, and because Cepheid variables are actually quite bright, they show up in distant galaxies. Now, at the turn of the century, they didn't know that they were distant galaxies. Back before about 1920, if I go back to, this chart here on the right-hand side, a certain Mr. Hubble, Edwin Hubble, was poring over a glass plate and looking for stars that were varying. And he noticed that there was one star, well, there was a nova here, the N, that was found to be varying, but they detected that as a nova. And there was another one up here, this little star here between these two lines, that was originally marked as a nova. It was sort of varying, but then they had to correct and say, no, hang on a moment, that's got more of a periodic type variation. And he wrote VAR, variable. And it turned out that this was a Cepheid variable. And using this arrangement here, he worked out the distance. And the distance that was calculated for this star here put it outside of our Milky Way in this galaxy here, which everybody in the room should be able to recognize is Andromeda. So that was around about 1920, and it basically grew the universe just by using the technique of photometry of variable stars and the period luminosity relationship here. So that's a little bit of that sort of background. Now, if we wanted to do this ourselves, and we can, you can do it visually. You can go out with a star chart, and there are various resources, various websites. There's the British Astronomical Association Variable Star section, and there's the American Astronomical Association Variable Star Organization, which produce star charts of known variable stars. And you can go out and visually look at, once you've located that star, and you've got some known comparison stars that don't change, that don't vary, you can then visually try and infer how bright that star is. It takes a bit of skill. I've never done it. I wouldn't trust my eyesight, but if you've got a pair of binoculars and you can sort of estimate the brightness and see how it changes, you can make your notes and basically contribute to visual variable star observations. It's as easy as that. Of course, you've got issues with how clear the skies are, light pollution, all that sort of thing, and perhaps most importantly, your own bias. Does it look a bit brighter? I don't know. So each individual that does this will have their own sort of bias that has to be calibrated in some way. Here is such a star. This is for the prototype, i.e. the original Cepheid variable Delta Cepheid, which is that star somewhere, I think it's that star in the middle, and all these other stars with little numbers, the numbers refer to the absolute magnitude. So these are all the check stars. So if you find that star and you compare the brightness of that star with maybe one of these other stars that looks very similar, and see how that star varies over time compared with that star, that's basically what we're doing. And there are databases, like this is the American, the AAVSO, so the American Association for Variable Star Observations. And they've got a huge database now built up over decades of all different types of variable stars, not just Cepheid variables, but remember that variability tree right at the start, lots of other types of stars in there. I've actually become a member of that, so I can go in and do search, but actually this is available for anybody. You don't need to be a member. You can just go in and search for a star that you might be interested in, check whether it's variable, or you're looking at a particular constellation that happens to be in a good position, fairly high in the sky, so you're not looking through too much of the atmosphere, and then you could see what variable stars are available. And this is what you would get. You can then see an example of the star. So for Delta Cepheid, you can't read all of this, but it's telling you it's in Cepheus. It's telling you whereabouts it is using the coordinate system. It's telling you actually that all of the designations amongst all the other star catalogues, and there are huge numbers of them. I mean, with Vera Rubin coming online, with the Gaia catalogue that's already cataloguing sort of, is it how many, 1.5 billion stars, with accurate photometry information and position and movement and a spectral class for most of these stars. There's huge amounts of information. But now you think, well, we're redundant then, aren't we? But no, the point being that we can use that information to feed in and refine it. And it tells you the variability type, DCEP, that's a Delta Cepheid, spectral type down the bottom here, and the expected magnitude range, which is quite useful. This is easily visible with the naked eye, 3.5 to 4.4. You know, within a reasonable sky. It might be a bit of a challenge here. I'm not quite sure. Typically, you can get down to 6 in really good skies, but around here it may be a bit more of a challenge. Okay, so onto my side of it, which is how do we use our technology that we've got in our own back gardens, whether it's a small sort of modest telescope, maybe not even a proper astronomical camera. It could be, as I said, a DSLR camera, because DSLR captures red, green and blue at certain sort of broad wavelengths, which is quite important when you want to measure photometry. You need to know what wavelengths, again, going back to John's point, we're in the visual band here, but we need to know whether we're measuring it in green wavelengths or in red wavelengths or blue wavelengths. And for the research standard, it needs to be in what we call photometric standard bands. And you can get filters, basically red, green and blue filters that are specifically photometric filters. And they're actually no more expensive. In fact, they're cheaper than buying, a filter for light pollution filter, about 70 quid or something like that. And then this is where, for the astrophotographers in the group, you then do the same, you do exactly the same imaging that you would if you wanted to capture a nice galaxy or something. You have to work out your focal length, because you want a region of the sky where, there's your target, but you've got enough other stars that you've got some good comparison stars that do not vary. You need to do properly calibrated frames. Now, this is very important for science purposes. You need to make sure that you've got rid of any dark noise, any read noise from the camera, so that doesn't affect the photometric reading. You need to make sure that there's no optical artifacts coming through as a consequence of flat framing problems, and so on. You've got to make sure, of course, that you don't overexpose, so that starlight is basically saturating your camera sensor, because your camera has got to work in what we call the linear region. In other words, not, you know, the Goldilocks region, if you like, not too bright, not too dim, but nice and linear. And if you overexpose, you reach the top, and then it doesn't matter how bright that star gets, it will just be reading a constant number. And then you just keep taking some images. And then once you've got a stack or a set of data, so you've got lots of individual images of a region of the sky, just like we would if we were doing astro imaging, we then need to actually measure. And this is the photometry. Photometry is measurement of photons, effectively. And we do this through a technique that's called aperture photometry. So we've got, and there's a bunch of different sort of software apps that help us here. But we want to measure the light from the star, and we want to measure the background, the sky background, because the sky background is across the whole of the image, but we want to then subtract that from the measurement of the star. So we've got a pure measurement for the number of photons of that star. And remember, because of the optics, we think of stars as pinpoint, but actually the light that we capture on an image spreads the light of that star in a very characteristic, it's almost like a bell-shaped curve. It's slightly more complicated than that, but it's got a width, it's got a height, and it's got a width to it. So we want to make sure that we capture most of that. Theoretically, the width of that star shape goes on infinitely across the image, but by the time it's outside of the second sort of red annular ring there, it's pretty sort of minimal. And we can use software to do that, and I can always show, you know, do a real-time show how easy it is to do that. And what we get when we actually apply those circles, we get the profile of the star. So here it is, and it's reading 4,000 counts. So it's measured 4,000 photons, or ADUs, analog to digital units. Don't need to worry too much about that. But think about that as the number of photons at the center part of that star. Then the brightness tails off down to the background level there. And basically the technique is to work out the measure of the stars within what we call the source and subtract the background. And once we do that, for all of the different measurements over time is along the bottom, and brightness is along the left-hand axis there. We get all of these data points. And it's very important that these data points are not just a number you read, but actually they've got what we call error bars, because all readings have a level of uncertainty, and for science purposes, we need to measure that level of uncertainty. We do that with these sort of error bars. So the real value lies somewhere between those error bars to a degree of confidence. And that looks, well, yeah, okay, well, yeah, brilliant. So this is generally over a certain length of time. But what we can do is we can fold all of those images until we play around with the period. If we don't know the period of that star, because if we go back to here, it looks pretty random, doesn't it? But we can use some techniques, which we call folding, to think, well, let's do a test period. Let's put in, I don't know what it is on this one, just over 5 days, 5.5 days. So you put that into the program, and lo and behold, you get something that starts to look like a periodic curve. So we can then say with some degree of confidence that that is the period. So that's from that peak to that peak, and there's 2 cycles. It's 5 and a bit days. Yeah, and that actually is job done. Almost. In fact, what we submit the data that we submit is effectively a table with all of these values, and then we can go on and see our contribution. And we can do some analysis, we can do some clever sort of processing, and I say clever, the computer does it. Okay, we don't need to worry about this, apart from playing around with the period, but actually you can use the computer to do that, and it will come up with what it thinks is the most likely period. And in this case, it's come up with just over 5 days, which is pretty close to the trial period. I sort of knew the answer, but you know, to prove the point though, you can then run it through the sort of period analysis, which uses Fourier transformations, all that sort of clever stuff, to actually give you the most probable peak. The highest value there is the most probable period. And then, so going back to the period luminosity, you know, the number of days and the brightness and that wonderful straight line, you can then use that information and some of those values to work out the distance. And in the case of Delta Cepheid, I think it was this star, it was using that light curve data, 280 parsecs, which is 900, just over 900 light years away. 280 parsecs. You look it up, you know, in tables and so on. Actually, it is fairly close, just using those simple rules that Henrietta Leavitt worked out back at the turn of the last century. This is some of the data. How am I doing for time? Oh, it's not too bad. This is some of the data that I used for my project. It was only 16 data points. Ideally, and why it's important for us as amateurs to contribute to the data pool, is we want to get lots of data points so they can then be used, one, to just validate existing data, but secondly, see how things change over time. Because as stars' life cycles change, their physical characteristics might change. If their physical characteristics might change, their periods might change, and so on. So actually having a historic set of data is really important, actually. And a lot of these databases go back, as I say, certainly decades. So we can get that, and we can do some of the, this is the folded light curve. And for the star, it was purely an arbitrary star that I chose. It worked out the period was 14.6 days. And lo and behold, I did put it through the computer, and oh, guess what? It came up as about 14, just under 15 days. And using that information, I won't go into all of this detail, but using that information with these relationships, I could then work out an estimated distance that my star was 50,000 or 50 kiloparsecs away, which is actually an incredible distance. And I really questioned it. I wasn't convinced actually that was right. So actually part of my project work was to say, well, if you believe what it's telling you, it would be this, but actually I don't believe that, and therefore it's subject to further research and so on. But from various relations, you can also work out from the spectral type of the star, the effective temperature, right? You know, our sun has an effective temperature of, what is it, about 5,800 Kelvin. So spectral class G2V. But also the overall absolute luminosity, so that my star was 474 times more luminous than the sun. And from that, using various equations, things, I could work out that actually it was 36 times, it's off the main scale, it's starting to get big, it was 36 times bigger in terms of radius than our sun, just by using these photometric techniques. And that's just the pulsating stars. That was one particular type, which was a Cepheid. In fact, it was what we call an RR Lyrae, so it's a Type II Cepheid, whereas Henrietta Leavitt's were Type I Cepheids. And the classification is generally in terms of how long or short the period is. But there's other ones that actually amateurs can look at, exoplanets, planets that are drifting in front of are transiting in front of their host star. You know, it's the effect that when you see a moth or a small insect fluttering between you and a light bulb, your eyes actually notice the change. Have you ever noticed that? Yeah. Now imagine doing that with a telescope from your back garden that using photometry, you can measure that fluctuation in the brightness of that star, which is due to probably a very large transiting exoplanet that is going to be a few light years away. Amazing, you know, amazing that you can actually do this from your own back garden. And the importance here is actually working out the orbit, the orbital time of those exoplanets, knowing characteristics about the sun, about the star, like its mass. You can then work out from the orbital transit across the face of that star, where it began the transit and where it finished the transit, the time to orbit. If you know the time to orbit, you can work out the mass of that planet. So you're starting to do some real astrophysics here. Then we've got eclipsing binaries. This is where we've got two stars orbiting around each other. Algo is probably the most famous one of those types. And in fact, again, it's a visual variable. You can notice that with your own eyes, but you could measure it. And then we've got the cataclysmic one. So, you can look at supernovae and so on. The American Association for Variable Star has what they call a target tool. And this is where they will put their campaigns, and you can be on email alerts to be notified that researchers want you to point your telescopes in this area to contribute. There's a whole bunch of them, and so depending on where you are and where your position on the Earth is, it will limit what you can see. We're nearly there. Let's go. Okay, so eclipsing binary stars, we get sort of that's what's going on in the top right left-hand corner. We see the different dips in the light, and there's two levels of dip depending on how bright each star is. But you can actually measure this, and this was one I actually did. This is real data that I captured. This chart here. I think our battery might go on here. Yeah, this chart up here is all of the data captured that's available in the database. Here's some data that I captured the other day, and you can actually see this was 3 hours worth of data of that target star, which is HL or Riga, which is an eclipsing binary. And all I've done is captured a little bit of it. I don't know whether it's this part of the eclipse or the secondary eclipse. All I know is I've captured three hours worth, and that's submitted now. So that's gone into the collective. 90 observations, just 30 seconds. So 90 lots of 30 seconds. So that's that side of it. But there's other things that you can look at. Supernovae. You can actually measure. This is going back to our friend M101 again. And just as an example, this is a light curve done by quite a prolific observer, Ian Sharp, who's based on the south coast, but he's got an observatory a bit like Nick in Spain. This is 23 IXF, and he's actually observed that in 3 different wave bands, and actually seen how the profile has changed over time. This is sort of months of data now, 200 days of data. And he's actually been observing how that supernova, from its original sort of peak, or just after its peak, has slowly changed. But see how the changes vary according to the wavelengths. And that starts to tell you information about what's going on with that supernova. And he's also done, and John will bear me out here, if you can get spectrographic data as well, at different points in time, together with the photometric data, you start to get a really good picture of what's going on with that star or that supernova and so on. And I think that is it. Any questions?
Well, I've got to ask this. How was that folding process?
Originally, they would have drawn with tracing paper the dots at the points, and actually then tried literally fold. This is where the term folding comes. Tried folding them over. What you do is you set up a little spreadsheet and you put in some little equations that give you the phase based on a period. Period is the x, the unknown. So you put that in as x, and then you work out the phase, and you just keep changing that period, that x number, until, and you graph it. And I've got a very simple spreadsheet that will do this. You graph it until you start to see the semblance of a nice periodic curve. And when you see that semblance, and it's very often, it's quite sensitive. You might get to 12 days, and it could be 12.2 days. But if you go half a day either side, it's quite erratic. And so you have to narrow it down. But that's how you do it.
It's not very sensitive to other harmonics.
The folding and doing that technique is not that sensitive to other harmonics. Doing the computer-based sort of signal processing method, which is using Fourier transformations and lots of tricky modeling, you can then work out. In fact, I won't go back because I can't easily do it. But that graph that showed you the period, all the other bumps were potentially harmonics, because pulsating stars don't just pulsate in one period. Sometimes they have other periods that they're also pulsating in, and that can tell you about the physics of what's going on in the star as well.
Some clever smart is going to get all the data from the Liverpool Telescope and set up a little it's going to just keep
that little clever dick is sitting down there, but he hasn't got anything better to do.
Somebody do it. I guarantee it.
Yeah, exactly right. Any other questions? Or I battered you all into submission. But look, my key point here is anybody in this room who's got a camera and telescope can do this. All of that stuff is free. All of those applications and stuff is free. You can buy stuff, but actually, I pay a nominal $50, I think, to belong to the AAVSO, and it's a wonderful resource. It really is. That's great. Thank you.
Thanks very much, Liz. To comment from not just with Liz, but with both those speakers this evening, we've been fortunate over the time, thanks to Liverpool Telescope, to actually very prominent and very very good speakers coming on from outside the society, but just to show that what we have within the society, within our own members, the amount of knowledge and expertise which we can draw from and should do more often. So this evening has been an example of what we have got within our own environment.
We can say something to the audience. We're thinking in terms of possibly doing another members evening like this. And I did with this from the members talk would follow a main speaker and then usually much shorter. We're talking here about the talk of maybe an hour, 50 minutes, and maybe half an hour, something like that. We're perfectly happy to have another set evening in 2025. We have two potential slots at the moment. We're not quite sure which one they're paid because it depends which one. We're trying to capture one more speaker, and it depends to some extent when he will want to talk. If anybody is including speakers have an idea for set the talk in 2025, it might be January, but I can't swear that it will be January, it may be December. But if you do have a talk in mind, don't worry about the fact you haven't written it yet or it's not clear in your mind yet or whatever. If you are interested in giving set the talk, could you let us know in about the next 3 weeks or so? And I know that.
Does it have to be astronomy related? I'm thinking about doing beers around the world.
Yeah, whatever. But the thing is, if nobody wants to get that talk, it does clear it up to find a speaker, and these speakers, unlike you normally, do require quite a long lead time. So I know it seems very early in the day for next year, but if you could let us know in about the next 3 or 4 weeks, if you might be interested in giving us a talk, give us some idea of whether it be feasible to do this again next year. We'll be delighted to do it again next year, but we need to know if it's feasible. And that way, the biggest happens.
Yeah, so meetings have Astro or.
Well, you can contact my normal, doctor at peterjt, my doctor.com.
But we just need to know because
Yeah, so
we
we need to know.
need
that.
time for the speakers.
We've got most of the talk sorted out, and as I say, we still have these blue class at the moment. The other thing is, I don't know much
Oh,
about
that's
the
much, yeah, oh, okay, so in March, we're going to do a slideshow like we did in September last year, that was called Images of Summer. We had 45 images from 10 people in total. I'm already in touch with some people who gave me some images in September last year, the more people I'm going to contact them right now shortly. But we'd just like to get some images together for the, it's in the club member slot in March. So I do have some material already together. We're thinking maybe 5 to 6 maximum, 5 to 6 maximum per person. 1 or 2 people might just do 1 image or 2 images, but I think it was quite nice last year, wasn't it? Yeah.
I think one thing I want to emphasize is that the quality of the picture beyond the basic minimum. But beyond the certain what you might call basic minimum, the quality of the picture is irrelevant. What we want to do is to show your picture. So it might be your best picture, it might not be somebody else's best picture, but it's not a competition. We're not asking you to compare one person against another. What we're trying to do is to capture the spirit of photography in the winter. The sort of thing that you photograph in the winter.
We fancy that too.
I was going to say, lots of plans.
So lots of plans. So the period covered is the 1st of November roughly to the 29th of February roughly. And I'm already working on the slideshow. Peter and I will put things into, so put people into analytical order.
And that's the attitude piece.
Aesthetically pleasing, if they're calling it in the bleak midwinter, so. That's it. Yeah, I will contact people who contributed last year. I've already been in touch with some of them.
But don't hesitate, don't wait for us to contact you,
Yeah.
send them now.
Thank you.
Following on from that, as you might have already seen, is that as previously mentioned, in conjunction with our 30th anniversary, rather than as the photography competition that we've been holding for the last few years, what we've arranged in conjunction with Team Shakespeare is for the month of April to actually have a photography exhibition in the visitor centre. I had talked to with the centre manager and she agreed to that. So basically, along the same lines of what we were talking, is if any members would like to submit images of any whatever it's all us to do or related to astronomy or astrophotography, we'll get them printed up and we'll get them laminated, and we'll then put them on display. I've actually put the details in the notes, but just to say that as long as each individual image or the submit, we can just give a little notice to what the image is, any details about it, and they'll be attached to the image. And depending on how we get on space we're allowed, we can either print them up as size, like 10 to 4. That's basically it. Feel free, fill your books, no limits to the images. But say once we have them all in and we actually have surveyed what actual area we put them up in, I think we were allowed to have one there for the month of April. So I think I've put a date of Monday the 18th of March that we submitted. Give me time to collate them all together, arrange for them to be printed off, laminated, and a couple of months to be complete. And once they're all up on display, I'll show them. No. Okay, so it's not a competition as what yes, please, I'll put the address on there.
Do you want to be specific about the size, the file format? Because depending on that, the quality of the actual printing results could be quite variable. So we might need to get our heads together on that just to be specific. Okay. And depending on which printing company, because they will need to know that.
Yeah, well, I'll say I was in the local one for the town. I'm not sure we need specialists on to it. I'll just
If we want them to look good, we probably need to, use one that's experienced in that sort of thing.
so that'd be additional time for this kind
of it may be. I mean, the alternative might be if people have got printers and they're confident that that they can print them to the quality they want to show them.
So Tesco's and Raymond, they've got brilliant photo plates and they take all formats. Literally, you can go with an SD card and they do pings, tips, BMPs.
Yeah, I was thinking more about there can be a big difference
Yeah,
from what you see on the screen
yeah.
to what
But
you see.
they do a preview and it's like a Canon photographic center, so they balance the
Okay.
printers.
Okay.
So
Just be wary that what you might submit and what you see might be
it might
different.
be different.
I mean, is there any specialist printers of astronomical imagery?
It comes up occasionally on Astro social media that people that have printed stuff have got their favourite prints. But you know, for purposes of this, we could do some trial prints and see what they come out like. You know, and if they look good enough, and to the general public, perhaps it's not a problem. You know, but I'm just flagging it as a potential issue.
Yeah, that's fine. Well, I'll keep that date as the date on the 18th of March. I think the board should be one.
I was just looking for there's something who's never really up to the Photographic Society. What's his name?
Right, you think George?
George, yeah.
Yeah, George.
Yeah, let's go over.
But he might be able to, because he would do photographic competitions or photographic exhibitions and printing. He might be able to be the best person to sync up in.
I'll get in touch with George. Thank you. Okay. Again, regarding our anniversary, community looking at various ideas to celebrate it and record it for the membership. One of the things that we're looking at doing, as I say, is holding an event for the public in June, based on the theme of introduction to astronomy. We've done similar things before, you know, it isn't like a little day event where we actually put on displays and talks, and June might not be enough to photography and observing, but even if it's like solar observing, something like this and that. Let's do the date. First of June. Another thing we'd like to arrange, which we done 20 years ago in this facility, is a visit to the National Space Centre in Leicester. And this has been doing some research into. I've got some details here. But I can insert that one. But it can be anything from an organisation, from a minibus, or depending on the people. You know, we need to know from within the membership before we start making specific arrangements who would be interested. I think the minimum group is 15. I think this was saying. Group booking is a minimum number of 15. We've got all sorts of activities going on there. I'm not sure the journeys come to Leicester and back. There's been research already. But before we go ahead with that, we'd like to know from within the membership how many people actually be interested in seeing it. Again, looking somewhere along the May or June time. And so if something you'd be interested in, and we get a general consensus from the membership, then we can probably progressively move on. For a group booking, the minimum is 15.
You have to be maximum.
No, I think they're saying minimum was 15. Obviously, the more the merrier. And also, coming August for the meeting, we had meetings before where we had just observed and reviewing the features. This year, if the conditions are, we probably have to do a bit of a larger, like a star party, stargazing party. Again here at Thames Chase. All these things are so dependent on the amount of interest we have within the society and the support. If we've got the interest, we've got the support, we as a committee are quite happy to go ahead and do the logistics and arrange it, whatever. But we don't want to go and sort of claim things which the support or the interest within the society is not sufficient for it to be a worthwhile concern. So if anybody has any views at all or be interested in any of those activities, please let us know, and then we can go ahead. Another suggestion from the years, which sadly I did have some images, but we'll have to show them. It's having a commemorative T-shirt in society. I still am in possession of one of the original society T-shirts, which is years old, and unfortunately none of it fits me. Yeah, something like that, at least had a couple of those images, whatever. Again, we wouldn't want to go out and look at put an outline of can we produce to find out that they weren't really that much in demand. Again, something which we would like feedback or response from within the society. I'll be pushing an email out soon detailing all those with the actual stuff. Just bear in mind, this is sort of what I want to put forward, and we are looking for the support from yourself and the interest in that kind of reality. Okay. 12th of March, we are down to another outreach event here. Guides, sorry, Brad is running stuff. It's a bit of an early one, 5:30 to 7. If anybody would be free or able to come along just to help out with setting up scopes outside, if conditions hopefully are able to do some enjoyable reality, or just to help us with this setup, that'd be appreciated. And lastly, some of you may notice that I've set up at the back of the hall there. The Young Sea-Star smart telescope. Now you might remember that last time we had Jamie Carter give us a talk about smart telescopes. There was a proposal from Liverpool at one point that was made to consider one for the society. And we were in the throes of negotiating or discussing whether we should have it in the purchase fund, and that was happily superseded by the kind generous donation of management who was actually brought this scope for the society. So thanks very much, sir. Since we took possession of it, sadly, we brought it along to our last two outreach events, and sadly on both events. But we were still able to demonstrate it to them in the barn using. I'm still finding my way through it and finding it quite a lot of fun. And hopefully at the next outreach event, conditions will be fine to use it for them. If anybody is interested, I know individually showing some interest, but if they want to come along and see how it works or whatever, the more the merrier. As I say, it's the society scope we use within the outreach groups and the universities and whatever. But if it's something that we might find you want to just see for yourself, so we want to actually find these things. Okay, so unless anybody else has got anything else this evening, thanks very much, and hope to see you all next month. Thank you.